Okay, so maybe just make a start. So welcome back to the ARIVE lecture series. And today Tomasz will talk about digital twins, and he will actually give a live demo. So that's quite exciting. And I just hand over to Tomasz.
Thank you. Thank you. And Conor will be showing actually the live demo. So he's with his laptop sitting behind and hopefully fingers crossed for the live demos that it will work. Okay, so let me just see whether, I hope you can see the slides properly. Let me just set up the screen so I don't have anything in here. So yeah, so again, like during class lecture, we were saying what is our main goal of Epicenter and as well my visual analytics team and Data 61. So solving complex problems using visualization, computer graphics, and modern computational platforms. And we're delivering lots of interdisciplinary tools. That's one of the main reasons I wanted to actually talk a bit about digital twins today, just to give you a bit overview of what digital twins are and show you some of the examples and animations. So today, lecture will be more about showing some use cases, and I hopefully will be useful for our community. And if you have any questions, of course, feel free to flip us email or message on the Slack so we can respond as we go. Okay, so as you know, we have like 4 industries over many years. We are now Industry 4.0. So the aspects of cyber physical systems, Internet of Things, and networks, everything is connected to everything else, is actually more and more relevant in today's world. One of the aspects that our ARIVE network is using in the Industry 4.0 will be situated analytics and AR applications, for instance, which will be very useful for Industry 4.0, but as well using VR and connections with all different sensors you have spread across the networks, and how you can actually use this interconnectivity to, let's say, teleoperate or monitor or get the status from different cyber physical systems. So we have definitions of digital twins. There's actually many definitions. Those are like 3 selected ones. So for instance, SAP was defined it as a digital twin is a virtual representations of a physical objects or system. Or for instance, GE was saying digital twin refers to a digital replica of potential and actual physical assets, physical twins, so like kind of real world scenarios, processes, people, places, systems, and devices that can be used for various purposes. An example of that, you have digital twin of a wind turbine, which is like in the real environment, it's like a real system, but you can use virtual representations of the turbine and actually, for instance, monitor the status of operations, teleoperate, or get the readings from different sensors that are built inside and stuff like that. So we have 3 different types of digital twins. So the first type is called status twin. So it's basically used for basic condition monitoring applications. So if you have, let's say, like power plant, you can monitor different piping system pressures in the pipes. You can monitor, different aspects such as thermophysical, like temperature, humidity, and stuff like that. And it's usually used with visualization tools. So if you are having status twin in VR, for instance, then you combine basically the power of VR and as well immersive analytics to present the data in 3-dimensional space. Then I hope that will work. Yeah, okay. The next one is operational twin. So that's basically more for operational scenarios. So it can be used by operators, decision makers, reliability engineers, just to make decisions in the real operations. So it's linked to different types of operational workflows that could be part of like industry settings that allows you to control different parameters and as well optimize how you change the parameters from, let's say, remote locations, for instance. And the last but not the least is simulation twin, which leverages lots of simulations, computational and simulation sciences and modeling areas of, let's say, science, where you can simulate different scenarios, and you don't necessarily need to actually have everything in operations. You can pre-simulate different scenarios and select the most optimal setup, and then basically use that as a ground truth for real-world scenarios. Lots of simulations are linked with artificial intelligence capabilities as well today. So all of those things are very interlinked, and I'm going to show you some of the examples of that in a second. Yes, I wanted to show you actually like go on the deep water and show you types of digital twins that were done by, that was like the project I was part of like many years ago in CSIRO, when we had, you know, like we were trying to automate the shiploader operations. So it was basically like Western Australia. You can see, you know, like it's Australian outback, so the colors of the ground is like really, really orange. And then we have like some conveyor belts coming in. And then basically this big bulk carrier shiploader is coming to the port, and basically all the stones going on the stones are being smashed and going on the conveyor belt to the hatches on the bulk carrier, right? So what we tried to do with this particular project was build kind of digital twin replicating the operations of the shiploader and shiploading of the iron ore. So you could see this is like what the operations were happening. And before our projects, all the operations were going from this little booth in here. And we basically moved the operations to the remote locations. It was like, I think 2 to 3 kilometers away. And this small little building with air conditioning built in and proper visualization systems installed to teleoperate the whole operations. So it was the time where perhaps some of you know this point grey camera, which is called Ladybug, that was allowing you to capture 360 degrees. So it was just the beginning. This camera was much better than any other like consumer grade cameras that we have even today on the market. So it's able to collect videos with more than 80% of full sphere. And it has like 6 cameras, like 2 megapixels Sony CCD. And the limitations of that camera was that was only capturing that on 15 frames per second. But basically one of the things what we wanted to do with this particular operations, we wanted to observe from these locations like one-to-one scale scenarios when the ship was coming to here and making sure you can see the operations as they were going. So we're using for that one, of course, this Ladybug was actually installed. So you can see the installations of Ladybug. It was installed with some kind of, you know, like glassy or plexiglass like hemisphere. So be able to actually look in the surroundings. And that was like live streaming the video to remote location. And then we had like in remote locations, you have like a computer and joysticks who were able to operate the whole operations and field of view. So you can see, you know, this is like replicas in the lab that we were doing, and you can see another Ladybug in here, which is Blade. That was the next version, and then we have like stuff in operation. So this is done from the mining side. Then you set operator sitting in the front of hemispherical dome, and the hemispherical dome was used for the main reasons that it was able to simulate very nicely, you know, like 180 degrees field of view. And the size of the dome was carefully designed as well to make sure we have some kind of scale one to one. So sitting like really in the office, you could feel like being really on the mine site and teleoperating the whole mining equipment. There was like lots of processing done as well on the data. So the whole installation on the above the conveyor belt, we had as well like different laser scanners installed. And so laser scanners were constantly scanning the whole environment and giving you massive amount of point clouds that needed to be post-processed and used as a ground truth for, let's say, updating user interface. So that was the user interface we built. So basically you can see, you know, like virtual reality, very, very simplified, but the whole idea was to read the tonnage of the hatches in an automatic way. So the way how it worked was when the ship was passing through and we were loading the iron ore, we could see the tonnage of the hatches and size of the hatch or tonnage of the point clouds were evaluating for us, you know, there's some AI algorithms evaluating for us like the tonnage of that hatch so the UI could be updated. And if it reached the certain threshold, then basically you could go to the next hatch and stuff like that. So that was like operational kind of twin that was operating in the mining side. And this is showing like the screen. Perhaps you've seen IDOM in your life at least once, where you have like the big screen and you have like the projector sitting behind the screen and spherical mirror in the front of it. So this setup was done for the purpose that the user or operator was able to actually operate directly from the front of the screen and not seeing any shadow casting on the screen if you had projector sitting behind him, right? So that's why it was this way. And the scale of this screen is actually quite large. So you can see sitting in here, you could actually use your body gestures to interact with the system. So that's why it was designed in this particular way. And of course, there's like the whole processing pipeline. So it's very, very sophisticated kind of system in the operations. It was used in real scenarios, of course. So it's not like something that we often simulate just to simulate the environment. It was actually like a real environment. So we had like 6 laser scanners. So it was the scanner that was capturing those point clouds. Then we had one like kind of industry grade accelerator. They were quite expensive those days. It was like $2,000 to $6,000 per each. And they were measuring force and acceleration. And then basically by integrating all of that together and installing actually 6 laser scanner of the Pantilt unit, you could actually get the positions of all the mining elements and then basically recreate them in virtual reality. So you could actually see it in remote locations. And this virtual reality was very, very simplistic, as you can see. But bear in mind that this project was done in around 2010. So it's kind of, very, very still impressive, to see how you can teleoperate this kind of mining equipment. And you don't need to have very sophisticated computer graphics to actually represent the whole scenario as you go. Okay, so that was one example. Another example I wanted to show you is something that we combined like VR gaming, GPU, and stats together, which is basically building. It's not typical like digital twin, but it builds digital twin of representing like how the jaguars are moving in the jungle. So the whole idea was we sent a bunch of different statisticians and mathematicians to the jungle in Peru. And we equipped them with a bunch of different cameras you perhaps recognize from this picture. So Raikkoch Theta, for instance, you have like GoPro camera on the rig, and we had also like Gear VR, for instance, in front of this guy in here. And basically what they were tasked for, they were tasked to go into deep jungle where almost people never go, and capture different images in 360 to use those 360 images as a evaluation or whether there is some kind of evidence that the jaguars went at particular locations. So they go into the jungle and trying to map different parts of the jungle, and based on that use geostatistical methods for replicating like possible movements of the jaguars. One of the problems they actually were facing was because it was in the deep jungle, so there's like not many people living there. So sometimes they're traveling for 3 or 4 days without like electricity to recharge of the equipment. So every couple of days they were able to go to local village and steal a bit of electricity from power generator to recharge all the equipment. And to give you a bit of feeling about how it was in the forest, so this is like a small, sorry for the resolutions, it's not the best resolutions in terms of as well. Ways of stitching the videos was very, very difficult because it was very, very humid as well in the jungle. And you can see some artifacts actually on the movies. I just go a bit here, so you can see there's like a bit of disparity between different elements of the GoPro rig for the reasons that the humidity was actually changing the optics on the surface, and depending what was the temperature and humidity, the team had really problems to really stitch. You had to do it really manually, frame by frame, to actually match the images. So you can very clearly see that one in some of the artifacts going in here on the sides. So that gives you an idea that traveling as well sometimes along the rivers. That was very, very good. They were looking at different animals, capturing different data that was used really later for conservation and research. And we have a couple of publications actually in that space. So if you're interested, very, very welcome to have a look. And then basically what we did for just proper release just before Easter break, I was like almost now 5 years ago, we released like very simple VR installations that was released together in the Australian and basically it was giving you opportunity to install the applications on the Samsung, for instance, phone. If you had Gear VR, you could actually explore the visualization in the phone. It was transferring you to different locations of the jungle. So it was like very, very simple, but it was bringing lots of actually positive feedbacks from the community, especially for educational purposes, to see how the jungle looked like. And the outcomes of this project was, of course, some geospatial models showcasing you how the jaguars are moving in the jungle. So basically, using VR, you could bring the jungle to the scientists rather than scientists to the jungle, right? So how much cheaper is that? You send like a small group of people, and then you can do massive research by using expert elicitation, experts from across the globe to actually tell you what they're seeing in front of them just using VR, which is super, super powerful. Okay, another type of digital twins you can see in Epicenter if you visit Epicenter at one stage is something that we call it like immersive prototyping example, and this is basically like projects that we're doing to plan the metro station. What you're seeing here is a technical drawing from kind of like a CAD system that was imported to our HEVs. And then basically all the stick tags are representing simulations of the people walking in the train station. The whole idea was that the designers who are coming to the space are seeing the whole metro station and the scale 1:1. And as they go, they can see simulations of the crowds. And basically based on that and some other factors, they can make very informed decisions about how to design the whole space. Okay, so that was another example. This one is another example where this is UNSW campus, and UNSW campus we have collaborations with Professor Cici Zlotanova, who is doing lots of scans of the campus, and this is showing like the voxel space of red building, it's like red center, and as well like flying through, and the whole project is basically developed as, this is like the initial version of digital twin, which is not very dynamic, but in the future we're planning to actually use dynamic scenes when you can actually see people walking around and having different readings from different sensors and travel through the whole campus for many different purposes. For instance, you know, when you have people who have like some problems with you know, like let's say walking, or you can basically navigate them through the campus so they're not taking, you know, too long ways to get from point A to point Z. It's like many use cases you could use digital twins for that. Okay, let me see whether I can go to the next one. And the next one is something which is called Australian Square Kilometer Array project. So this is basically a project which is currently the fastest survey radio telescope design engineered by CSIRO in Australia. So it consists of 36 antennas, and they are distributed across a 6 diameter area in Western Australia. And basically the whole idea is to observe the outer universe and use radio frequencies to reconstruct the whole sky. And you can find UFOs perhaps, but as well like galaxies, constellations, and stuff like that. The whole setup is actually set up in something called radio quiet zone. And basically, so that's basically zone that Australia created to protect from any radio noise. So trying to make sure that whatever signals all the antennas are capturing, they are actually very, very clean in a way. And basically for that reason, digital twin is a good way of monitoring the status of this kind of very, very sophisticated hardware infrastructure, but as well gives you opportunity to as well to teleoperate if you need to change the angles of the antennas when they are looking and basically see how everything operates as it goes. Okay, and I think there was another one that was the very first version, so that was like in VR. So as I call it from VR, so it's not very kind of, it's a bit jiggery, but it's okay. Basically, one of the aspects of this of the simulations as well, our team and collaborations with CSIRO, Data 61 CAS and Epicenter, we're looking as well and building simulations of the Australian landscape. So you can see the landscape is very, very like it should be in Australia, but as well simulations of the sunsets, sunrises, and shadows, and using like more like realistic computer graphics for simulating all these examples, and as well like star constellation. So as you can see on these animations, you have some kind of, you know, timer being visualized, and basically on the timer you can set up that, like, let's say 100 years from now, and it will show you how the constellations will look like. So it was actually done in a mind that you could actually accurately predict how the sky would look like in the future, past, or the present, if you need it. And then you can speed up as well. So you could see different types of antennas. You can see the stars. I hope through this video streaming is going not too bad. And then fly through it. So we have like the versions which is running on Epicylinder, which is version which is running on VR, and it's using high-end visualization system that we're gonna show you in a second how you can start using from today on if you're interested. And I think one of my last examples, just to show you as well some of the scenarios of kind of IoT and how you can use them for, let's say, education. I know we're gonna be having talk next week about education, I think, like Holger will be giving talk, if I remember well, from the schedule. But this is one of the examples how we use gamifications to attack something called natural disaster land. So that was basically like done in collaborations between art and science kind of students, where they were designing some kind of scenarios when you have different simulated environments. In this case is, you know, a bunch of sensors that are sensing different things. I'm gonna show you in a second in animation. And basically you as a end user, you have to play game to resolve a certain thing to save the people. So basically you are in natural disaster and natural disaster land, which is the name of the VR. And basically, just waiting when it goes, you have like a board when you make decisions. So what you're seeing here, you have to save people. So you have people sitting in the middle of the board, and then basically what you're getting, satellite is indicating there's like big wave coming in. So you need to move the people to the forest. And this is not the best capture because I was recording that bumping on the table and stuff with VR, unfortunately. It was done in rush, so I have to redo it perhaps at one point. But you know, once you save the people against the wave, then there is a fire in the forest. So what you need to do, you just need to do another thing. So you need to click on you know, like the helicopters, and the helicopters with water are going there and just removing the fire from the forest. Right, and the last but not the least was once this is all done, then you can move people back to their homes, and then you basically save the people. So that's very, very simple linear storytelling done in very beautiful way, in my opinion, and it was quite popular across all the people that are playing with this particular VR installation to actually have some kind of, you know, tasks, and how using this task, especially how you can educate kids about the importance of different sensors that are sensing our universe. So this is basically like the last slide that I have in here, which is of course our Epicenter team, and there's a link in here which is showing you like the link to HEVs. And now we're gonna switch to Conan, I guess. So Conan, I will stop to share, and if you can share your screen, are you there?
Yeah, I'm here. Let's see how this actually works. I've got multiple Unity instances open, so as long as I can share the whole screen, we should be good.
So we're doing live demo, so please be patient.
I'll keep things very simple, so hopefully it will go off without a hitch. Okay, cool. Basically, what I was going to just quickly go through, Tomasz has asked me to sort of give an intro to at least using HEVs. We've got these project pages where you can actually access HEVs at the moment. The build that I have up is the release that we did at SIGGRAPH Asia last year. We do have a newer version that I will be uploading soon. There's just a few little things I want to test before I push that. I didn't want to push it too early. So at the moment, you can grab the stable version that we have. There is a bit of an overview onto how it works if you'd like to read through that. A couple other labs have used it in the past. A couple others have looked into it recently. If you want to try it out and you have any questions, feel free to email me. It's conan.burke@unsw.edu.au. But the stable version that we have up there was developed to work with Unity 2018.4 and 2019.2, but it should actually work still with newer versions of Unity. However, the newer version that I'll upload soon actually has sort of more features and better support for 2019.4. And we have tried it out with Unity 2020 as well, but due to some of their changes as to how they handle XR now, it sort of broke one critical aspect for what we do here at Epicenter. So I haven't pushed through to that yet. But anyway, I sort of rushly tried to explain HEVs on Tuesday. In a nutshell, what I'll cover right now is just using the core component, which is, it allows you to create visualizations that can run on single nodes or on clusters, but also on just standard desktop displays or multiple projector displays, dome displays, cave displays. All of that sort of included in the core, and it's tried to keep it as simple as possible to use. So what I'll do, I'll just real quickly create a new project in Unity and just show you how to bring in the package. The package is available on the Bitbucket under bin. So we have two different packages in there. Grab either. So what I'll just real quickly do, and then I'll also show just a couple of projects that we've made using HEVs, real basic use of HEVs to make them work, and then they work on the cylinder, the dome, etc. So I'll do that as well. I'm just going to create a quick little Unity 2018 project. I'll just call it something like HEVs test. If you have any questions, feel free to ask while I'm going through this stuff. It's probably better to be a little bit more engaging than just be talking and waiting till the end. So feel free to ask questions while this does its thing. I guess one of the key standouts we have with HEVs is that we are trying to be fairly free with allowing other people to use it, at least with some of the initial systems we have. And I am trying to make it work on as many sort of different systems as possible, rather than just like some existing packages only work for cave displays or they only work on Windows, etc. So the HEVs will work on Windows, Linux, and Mac. And the newer version that I'll be putting up soon also on Android. So you can create projects that will port across easily to, say, Oculus Quest if you're using that, but also should work equally as well on a dome or a cave with minimal effort. So I have this Unity project, nothing really in it at the moment. So what I'll do is I'll just quickly add the HEVs package. So I'm just going to go with the 2018.4 package. HEVs is quite small with what's in it. We do have some example scripts and some example scenes. The versions that are in the package that we have up there currently, there's a couple of little odds and ends about them. So the new version that I'll be putting up has that mostly cleared up. But HEVs itself is a closed source at the moment. Discuss that further with Tomasz if you want. But it just works off a few DLLs that should work across multiple platforms. And the newer version has better support for Linux and things like that. I've also tried to keep it like as minimal as possible for creating a project so that you don't have to do a lot of coding. It will take care of the clusters and displays for you. The only time you need to write any scripts is when you would have written scripts normally if you're making a Unity project. Okay, so I've just added HEVs in. It's fairly small. There are some, well, there's at least one example scene in the existing package. The new package has a couple. There's some example scripts, but I'll go through and just create something from scratch. So I've got this basic scene that if I was to create this as a project and try and run it in, say, a cluster, it's not going to work clustered. It's not going to work for dome screens, nothing like that. With HEVs at its core, all you need is the main HEVs component. So I'll just create this empty game object. And all I'm going to do is add a component. And we've got just the HEVs menu for components. And what you're after is just the configuration component, which is fairly small. Tried to keep it as small as possible. All the ins and outs are kind of just hidden away. But with just this configuration script and no other changes with it, this is now prepped and ready to run for HEVs. HEVs is pretty much controlled just by a JSON config file, which there is one provided with the package. So I'll just look at that. So what this JSON script does is you use it to describe all of the different sort of visualization installations you have at your site or facility. And you can create inside that variations on them. What I mean by that is, although we have the epicylinder as an installation, we can create a version of it that will run as stereo 3D, or we can create a version of it that instead treats it as a large 2D display that is 120 million pixels for some interesting 2D effects. It really depends on the project we're making. But what this does, this script or this config file just describes a bunch of platforms. With the platforms, we could have things like a cave, where we define the nodes that are in the cave. In this case, this is a definition for a single node, so a single box cave that might have multiple projectors hooked up to it. So it has a single node, multiple displays, and displays come in all different types. I'm going to be real quick with sort of describing this config file. There's a whole document with the package describing how to set this up. And I might try and make one from scratch real quick as well. But you can describe lots of things, lots of displays. You can have multiple displays on a single box, multiple boxes with single displays. Nodes don't have to be a part of your visualization cluster. For example, our master in the cylinder is not actually one of the 56 screens in the cylinder. It's a separate control box. But you can have it where it is a part of the cylinder. EPFL in Switzerland, for example, their cylinder, their master node is one of the nodes in the actual cylinder. And it all works fine. You're able to just create these different configurations where you're describing the installation you have and how you want it to work and behave, where you've got options for sort of cluster options, synchronization options. Do you have hardware frame syncing with NVIDIA hardware or not? All these different options. And then you can create sort of inherited versions of sort of option configurations. And you can contain that all in one file or multiple files, it doesn't really matter. At runtime, your application can read one of these scripts and reconfigure itself. And you can change what script that is at runtime. So I can create an executable that uses our config file here, hand it to you, and you can tell it to use a different config file without having to recompile the project. So what we've got in Unity is, now that I've got this configuration component, by default, it is set to use that script that's in the streaming assets, but you can just tell it to use a different file if you want. And you don't have to, because at runtime, you can change it on command line, but where the benefit comes is that you can choose to preview your platform, your installation inside the editor, which can be helpful with trying to place things around to make sure that it fits properly. For example, if I chose the target platform to be the epicylinder, then it will give me gizmos to display each of the actual screens in the cylinder. I could, for example, also go to a dome, in which case I've got the dome set up. Now, one thing as well is that If you're used to VR, you're used to having sort of a scene origin as well that describes your play area. It's very similar with this, in that all of these displays are then based around the camera, but you can sort of detach that. So other main things that you might use in your scene is actually stuff to define a scene origin. For example, if I was just to create another object, call it my origin, reset it. What I can do is Heads will have then sort of a scene origin component. And what that does is it treats your entire installation space as being origin to that, meaning your tracking space, or if you've got a tracking system that uses actual trackables, or if you're using XR, then it's all based on that, but so are the displays. What I'm going to do is I'm just going to set up a simple little scene. I'm going to put the camera attached to that origin as well. Just bring the camera back so it's actually centered around about my height. What I will also quickly do is I'm going to set this up as sort of a scene where I could just move the camera around real quickly and just show the code, the small code changes you would make to have that work properly across a cluster, etc. So there's slight changes to how you use input. So I'm just going to quickly add a plane just for the floor. Reset that. Make it a little bigger. Give it a texture. I've got just a little sample texture I can just chuck in just so it looks a little better. Great. So I've got this little thing set up. And if I wanted to make this thing move around, I would need a script that would push it forward and back, for example, if I wanted to just do that. So what I could do, I'm just going to quickly make a new script. And if you've used similar systems before, I think VR Cluster, Get Real, etc., then some of the code changes will be very similar to that. Just going to create a little test script. And what I'll do is I'll make a script that can move this thing forward and backwards really, really quickly. So what you would do inside Unity, normally you might have something like just a speed variable, something real simple. And what you do is during update is just have something like, if you're using input and say, I'll change that, I'll do it this way. You had input and you were just getting the axis for, say, by default, Unity has like vertical in there. That's probably going to be good enough for us. So we could just go vertical. And what you would typically do is something like maybe transform, translate, and we'll just go based on the transform's forward direction, multiplied by our axis, multiplied by our speed, typically. And you would also most likely use like delta time in a real sort of naive sense to make it go forward and backwards. So that little test script on this thing, if you were creating a Unity application and you wanted to move something around, oops, one sec. That's because I want to explain that in a moment, but I'll just switch that back. So you probably can't see it on the stream, but I am going forwards and backwards now. But that's good for a single node. If we were running this on a cluster, every single machine is actually going to be having its own input and expecting to move that thing itself. And what we want in a cluster is that all the input actually comes from the master. And the way that we do that in HEVs is simply we've got HEVs wrappers for all of Unity's input and time. So all we need to do is just go HEVs.input, and even with time, because then we can get the time from the master, is just HEVs.time. And now this thing works exactly the same for us. It looks the same. It looks like nothing's changed. But this application would now work perfectly fine in a cluster. Doesn't matter how many nodes you have, a couple of nodes, many nodes. I've run many clusters on my laptop and PC together, or the big one. And that was it. That's all I've needed to do to make this thing work in a cluster, at least in the Unity side, is just set up to use a config, give it a script that will move it, and we make this thing, in our case, have a scene origin. And that simply means that, yeah, all cameras and everything are based on that. What you can do in Unity as well to preview your what your thing would look like is sort of what you saw just before. You can set up in your config different platforms. In this case, I've got one set up for a dome. It will capture like a fisheye image, and you can kind of get an idea of what it's going to capture. There are options to actually, in the config, change it so it's going to capture above or below. So you could just set up sort of like with our cylinder, it just goes around, and we've joked about putting a dome on top, and we could quite easily create a config file that actually will tilt the camera for that node to point upwards without having to change anything in our Unity scene. It would just still work. But when you run this, it will actually give you a preview of what you're seeing for the dome. So that, you know, it'll visually preview what you want. It'll work for all the different displays, and it will work clustered. One other quick little thing to do is you would typically want some sort of tracker, say tracking just one thing in the cylinder, or we can broadcast the XR trackers over VRPN. We have a tiny little script that we can give people that'll do that for you. But if you wanted to track something, it's quite easy. I'm just going to create an object that I'll call, say, wand. And what we've got in HEVs is various trackers. There's a few other scripts that we have, but we have some trackers. I've renamed a couple of these in the newer version, but you can choose to just grab a very specific type of tracker for your project if you want. But you can also just use this tracker manager that will actually sort of encapsulate different types of tracked input. So I could, with this, tell it to be a wand, which would be defined in my config file. But also, if it can't find the wand in a config file, it can fall back to something else. So I could have it fall back to, say, an XR tracker. If I'm running this executable in virtual reality, it will just fall back to using whatever I tell it to use. And these are just default XR trackers. Or I can tell it to use a mouse in the editor, and then it will basically, you know, trick it to thinking that the mouse is your tracked object, which is useful if I wanted to, say, just add a cube on the end. I'm going to put that cube in front, and I'm just going to make it small just for now. And what that would do, probably can't see it because it's too far in front. Bring it back a little closer. Is it actually, it'll map sort of the mouse in a way across. It's got this weird aspect happening, but it will map onto the display in Unity, so you can at least get a preview of what it would look like. But that tracker would work the exact same then in the cylinder with an actual tracked object. And there's a few other couple of little things just before I jump into showing some projects you can do. You can do sort of RPC calls if you are inclined to do that type of thing, where you can then have the master execute stuff if you want all the nodes to load something, for example, or you want the nodes to tell the master that they've finished loading something in, or they've finished processing their own data. They can communicate to the master that now we should change our visualization. All those different types of options are there. You can just call whatever you want. Functions can be executed from nodes just by calling RPC calls. You can do spawning calls so that objects can be tracked, and objects themselves can actually be tracked in a cluster quite easily. They have this cluster object component that by default tracker managers will use it, scene origins use it, and it basically will register any object with cluster object components, and they can be synced. So you can have transform synced, you can have just the position synced or just the rotation synced. Particle effects in Unity will also should closely match up. Unity doesn't give you much control over its internal timings of animation systems and stuff. You can, but it requires sort of custom code on your your part. So I'm trying to limit that. So we just kind of adjust Unity's internal timer. So that's sort of just a quick rundown on at least adding HEVs to a project. Most of it comes down to setting up your config, of which there are lots of options. There's lots of stereo options. There's lots of ways for it to apply blending and warping for projector-based systems. And if you're running it on VR, nothing actually needs to change. You just create the project, and when you execute the executable, if you've added VR to it, it will work in your VR system. But that same executable you could run within the cylinder. And all of it then is just run, like you just do a build normally, and then you would just run the command line. And in the command line, there's just some arguments where you can tell it to use the config file from a certain location and a certain installation.
And now we're slowly out of time, so just show maybe some fancy demos.
That's what I'm jumping to now. So we've got just a couple of little demos that we usually run. If you've been to Epicylinder, you would have seen this shaded toy one, where the scene's just set up so that every pixel gets filled with a mathematical function to decide its color. So there's no geometry. It just, every pixel goes through a math function to decide its output. And when it comes to the HEV side of it, we just have a basic setup where there's a scene origin so we can move around. There's a wand so we can point in our direction. And it just loads up the HEV's config if we want to run it somewhere. And what this demo then would be, which you've seen before, this is the shaded toy stuff Tomasz shows off a lot. We've got here, it looks like the ocean, but it's just mathematical functions. You can move it around. The movement's based on the mouse at the moment, but if we're in VR, it's based on sort of your pointing direction, or you can have it based on your looking direction. And this is just then running, mathematical formulas on every single pixel to decide its output color. So it's a really, really simple scene. And all of these sort of shaders, sort of implementations from Shaded Toy, which is a great website if you haven't checked it out. So I won't describe all the techniques because Tomasz has a lot. But what you can do is this same executable will run on all our various platforms. We could just tell it to be a fisheye, and when I run it, it will look like a fisheye. And it does apply the warping correctly. And then this can be displayed using one or more projectors within a dome. That's sort of just a really cool demo that we usually show off. Usually impresses a lot of people, especially since we're on an art campus. And the addition of HEVs to this was so minimal, and it just works flawlessly. It uses RPC calls to change the shaders on all the different nodes. Whereas I have this other project I can quickly show that this one is actually, there's nothing in it to control synchronization. It's just every single node is using input to load up. Oh, no, here's where we suddenly fail. The gamepad's decided not to work. Well, that's frustrating.
We have slowly to wrap up, so like.
This one was just a simple little project done with NMI, which is the National Measurement Institute, to visualize nanoparticle scans. What was great about this one is we're able to take their data, which is typically just drawn. I won't be able to change without these buttons working on the controller. So that's frustrating that oh, I just realized I'm grabbing the wrong controller.
There we go.
There we go. So they've got this machine they built to do scans of nanoparticle surfaces. In this case, we're looking at something that is less than 0.01 millimeters by 0.01 millimeters. It's absolutely minuscule. But the output of their scan is usually a few million points that they turn into an image for publication. And the images are typically something like this, but downsampled.
No, we're not seeing anything. At least I don't see anything.
You're
you're just talking to this beautiful photorealistic, you know, like black pixels on black background with lights off.
Yeah, for some reason it is.
But believe us, it's very, very hard. Yeah, okay, yeah, something happened with it.
Yeah, I mean, maybe we can just wrap it up so that we have still a bit of time for question.
Yep. Yeah, ask any questions.
Maybe
I'll
fine.
play around with this thing.
So maybe we go with questions. If we have like 2 or 3 minutes more, then Conan can
Yeah, I think it sounds good.
Ask questions. I'll just play in the background what people ask.
Okay, awesome. Thanks a lot for the presentation and the live coding. I think this was very impressive. So I will maybe just ask in the room here if there are there any questions. I can mute mine. Yeah.
So just a,
Sorry.
Feedback.
maybe so. Thanks for the talk. Just a quick question, actually, with one of the projects, and maybe Tomasz, you can answer that. So with the I think this is what you call the Twin City one, so the voxel one.
Yeah.
So is that also running? I guess it's also running on HEVs, but it's basically, for example, this whole let's call it the voxel engine. Is that part of what you released, or can you tell more about it? Is there also a point of?
Yeah.
Is there a publication that you can point to?
Yeah, there will be publications coming out. So we're trying to publish whatever we have. The approach is some of the like less, let's say, industry-based, like often projects we run, as you know, they may be, you know, like the industry locking IP, so we cannot release everything. But the approach we're taking, we have some of the projects, actually most of the projects we develop, we have this app layer that we were talking during our last talk on Tuesday. Well, let's say it's a voxel, right? We develop the routines for the visualizing voxels for a particular project, but at the very end of the projects, we actually like merge the API with the whole HEVs. So you're gonna have a API layer that's gonna be distributed with HEVs in the future. Perhaps with the voxels, we do have actually lots of magic now at the moment that we're trying to increase the speed of rendering and unlimited number of point clouds or voxels, and gonna be perhaps another half a year before we can release that. But if you're interested in having collaborations, I'm very open to talk to you offsite, and then we can discuss. If you're interested in that, why not connecting dots?
Yeah.
Okay.
Thank you.
Yeah, you're very welcome. And all the projects you've seen, actually, if you're interested in having some kind of, you know, access to some of the APIs, just please contact me and I will be able to share all the goodies with you guys. And as well, of course, HEVs. I would love to see you using that, and we can actually make it, you know, like ARIVE, you know, like you need to use, if you are part of ARIVE, you have to use it. And then we have, you know, like this lab from New Zealand and Australia. I'm just kidding. You know, if you wish, it's optional.
Awesome. That sounds very good. Any other questions here from the room? I don't see anything here, and Holger, we have maybe time for one last question.
Oh, is it one last question? The last question?
No,
I
you
don't want to steal the last
that's
question.
All good.
My question. Yeah, my question is actually a question which is more for my students here. So because they always tell me you can't determine really the absolute, you know, position orientation of, let's say, an HTC Vive or more so an Oculus Rift in space. So how did you solve it that you really get an absolute position in real space with an Oculus Rift and not just a relative position?
It's still very much relative positions.
Oh, okay.
Yeah. So that's sort of what the Scene Origin is trying to solve for some of those cases. We keep having lots of different issues with the different XR SDKs that Unity keep using. We're hopeful that since Oculus have at least said that they're going to be properly supporting OpenVR, that we could just move to sort of using based on that. And with the changes that Unity have made in 2020 for the way that they do all their XR stuff, I haven't explored any of the latest changes, so they might have improved how they do it at least. And then in our non-Unity version, very much just relying on OpenVR at the moment.
Yeah. Yeah. Thank you, Colin. And also, I have to second what Steffi said. I always liked it when people do live demos, right, without any safety nets, live coding. Great stuff. Thank you.
It's very minimal what I did. I didn't want it to break too much.
Oh, it's good, and I hope it at least showed you, how easy it is to put your VR installations to like big systems like Epicenter when you have 29 nodes connected and communicating with each other.
And soon we will have the collaborative component available that people could make use of. That means that we could have you guys running stuff in VR while we're running the exact same thing in the cylinder, and we can interact together.
Yeah, that's very impressive. Very cool, and I hope it motivates a lot of people to get into it and use it. Thanks a lot. So we maybe just wrap up then, and thanks again the speakers. Thanks a lot.